Hello there and welcome to SkyTour LiveStream here for April 10th, 2019. I'm here with Daryl, of course, our wonderful, ever-present astro friend and friend of the program. How you doing, Daryl?
I'm good, Mark. How are you?
Just fine, thank you.
Hi,
Maureen
Maureen.
Maureen makes an observation. Looks like the M87 black hole got everyone here. That's somewhat true. I'm at a loss to explain what's going on. Maybe people are thinking that Elon Musk's got a rocket going up tonight, but he scrubbed it till tomorrow.
Yeah.
So we'll see what happens. We'll just keep going. It'll be in the record books. Not sure.
You know, I'm sorry.
No,
those
go ahead.
SpaceX launches are about the funnest things I have seen since I was a kid watching space launches.
Yep.
I love watching the landings on those.
Oh, me too.
The Falcon Heavy launch they did February last year, I thought that was just spectacular. It's like it was choreographed or something.
Oh yeah, they landed together on the pads just seconds apart. Yeah. Yeah, indeed. I want to welcome Maureen and Shep here. It's nice to see you guys. And we're just checking out the moon here before it sets. We have other things to look at, of course. But we'll be back to it. And back to looking at other things. This is my last stream for the weekend, and then I have to head to Arkansas tomorrow. I have to do a talk down there tomorrow. I'm sorry, not tomorrow, but Saturday. Kind of a good primetime talk. It's perfect timing during the conference, so it'll be kind of nice. That said, I'm very hopeful that we will pick up a few more listeners when we're doing our thing down there, and viewers, because I will be talking about the SkyTour LiveStream and what we do here. Quite a bit, actually.
Cool.
Yeah. Yeah, so today, Daryl and I and Amanda, we had a little after-event show over at ERRT Radio with Ronald. And the three of us discussed the black hole that was visualized finally and actually seen for the first time in human history. And I thought that was a pretty cool sight, to see that black hole. It was gorgeous.
Oh, yeah.
Yeah. And if you think about it, that is the very first time that a black hole has ever been imaged by anyone. We've seen jets and so forth, radio jets, that come from black holes, but we've never seen the event horizon of a black hole. And this was the event horizon of the black hole that we saw. It was stunning. Absolutely stunning. And that's one of the things I'll be talking about in Arkansas over the weekend is that very thing. Because it's very important to I guess keep people apprised of what's actually going on out there. Because when we have a capability to view something in a new way, like this was a whole new approach. This was basically long baseline interferometry, essentially, to literally make the Earth's diameter the size of the telescope mirror. And to understand what that means, well, here's an analogy. If you took a quarter in Los Angeles and you held it up for a telescope to view the date on the quarter, the achievement we saw today, showing the event horizon of this black hole 55 million light years away, was the same as if we had a telescope in Washington, D.C. that could see that quarter in Los Angeles and see the date perfectly clearly on that quarter. That's the equivalent accomplishment that we're talking about. Isn't that amazing?
It is.
It's just incredible. Yeah, so I'm pretty stoked. I actually liked watching this whole thing. I enjoyed it. I really liked to see the people talking about it. The doctors and professors that were there mentioning this were people I know of, never met, but people I know of, and they're really up on their game. Really, really good, and they're really, really good. So I was very pleased. And it's funny because people look at what we saw there and they say, that's just computer generated crap. I know it is. And the answer is, well, yeah, it was computer generated. Of course it was. You know, but that's just the way it goes, you know. And let's see if I can, let me see if I can show you something here. Okay, so we're going to take away this because my flappulators are all set and my granostats are okay. And I've already welcomed you to SkyTour LiveStream. So what I want to do, though, is show you the thing that's behind it. This is actually, this is the black hole in the background that you see there. And I will try to get that a little bit. Oh, that's actually a different image. This is the black hole. Let me see if I can. I'm trying to figure out a way to do this here.
I'd love to see that at a higher resolution.
Well, of course, you know, of course. But
I mean, I'm wondering about like that big cloud or whatever up there at about the 10 o'clock position. I'd like to see what that really looks like.
Yeah, that's true. I think that what we're looking at there is probably. Let me make sure I've got. Is this what I'm looking at here? Oh, that's what I'm looking at. Okay. So yeah, so this is actually the black hole that we saw today. Okay, now this is the event horizon right here. Never before seen. Proof of Einstein's theory of relativity. Okay, these right here, if you notice, they seem to be symmetrical. Okay, there's a jet coming off here. It looks like a jet coming off here. I'm not sure if one of these relates to the jet that we see coming out of M87. But, you know, at 55 million light years away, I can expect that it's probably quite difficult, you know? I can expect that, you know?
Yeah.
Probably not easy. So that said, I'm pretty sure that it's got a pretty cool, you know, future, and we're going to be looking at this a lot more, without a doubt. Now, this bright area here is something that was predicted also by Einstein. And we're actually looking at material, that is to say, photons, that are trapped in what's called the photon sphere around this event horizon. This area around the event horizon that, you know, actually traps photons. Now, what it means by trapping photons, since photons don't have mass, you would say, well, then how could a black hole with gravity pull anything that's a photon toward it? Well, it doesn't. In that sense, it warps space, and the photons are following space. So they have to follow that particular well created by this gravity field here. So these are photons that are coming toward us, okay? And these are on the other side that are going away from us. So it is Doppler shifted light. Now you might say, well, how come this isn't blue and how come this isn't red? Well, it's red, but you know, because blue light coming toward us is blue shifted and red shift going, you know, red light going away is red shifted. So, well, that's because this is radio waves we're looking at here. We're not looking at visual light, so we don't see the color blue and the color red. This is a false color. This is not the color that this looks at all. So it's kind of interesting. And so we're seeing the higher energy light on this side. That's the light that's been accelerated, that's actually moving faster, coming toward us. And this is the light that's going away from us and actually moving slower relative to us. And then this disk that you see here is actually the physical confines of what we call the event horizon. Beyond that, the warpage of space is so great that the photons end up circling within it because space is so warped. And out here, they have an equal probability of escaping or going into the black hole. Those that escape, we see, and they frame it like this. So that's what we're seeing here. And I just thought this was a beautiful, beautiful photograph. And it'll explain the shape here, I'm sure, over time. This could just be anomalous stuff based on the fact that you know, this is a sum of many, many, many images. But we'll see. You know, we'll see what happens. You know, I just wanted to show you this because I thought it was pretty cool.
I'm curious to see. I thought I heard them say during the press conference this morning that they handed out releases to the journalists and such in the audience, and that they have 4 images of the black hole at M87, and they evidently put all 4 images on the press release. I haven't seen any of the others yet, though.
Oh, I've seen the second one.
Oh, have you?
And it's a wider angle view of the same region. I mean, a wider angle such that this whole area here is about 3 times the width of my mouse pointer here. And so you see a much more extensive view of this whole region. You know, that surrounds it. Yeah, that's online. You can check that out too. I saw it.
And you know, I bet you $2 to donuts. Before the image was officially released this morning, they were saying we'd see either the black hole at M87 or the black hole at the center of the Milky Way. And obviously they went with M87, but I bet there's an image of our black hole somewhere there too. Hopefully it will come out sometime soon.
Yeah, and theoretically it could be better resolution. But the problem with that is because we are quote-unquote so close to it, there are more things that can go wrong. The black hole will move and be visibly moved relative to us in our viewing, because it's going to take several years, you know, of acquisition to actually acquire the data to show this. That's what they've been doing. So if the black hole does move a little bit, as it will, it'll gain mass perhaps, or it'll shift its energy output or whatever sometimes. From 55 million light years away, it looks pretty much the same. But when it's close to us, we can see all the minute changes, and it might make for a worse image than something farther away, which is kind of an odd thing, you know.
I think I understand what you're saying.
Yeah. Yes, Tim. This black hole brought to you by Krispy Kreme Donuts, where we bring you the best in black hole technology. You eat one of our donuts, and you lose all your weight. Not only that, it never comes back, and neither do you.
Hey.
Yep. So not bad. So anyway, that's just the black hole for today. And back over here in the regular SkyTour LiveStream arena, we have the moon out, which is approaching. It's a waxing crescent now. It's approaching the first quarter, where you'll see about half of it lit up. That's because it's a fourth of the way around its orbit. That's why it's called first quarter. And that's something that is, you know, it's something we as astronomers have to live with. There are astronomers that love the moon. They can't get enough of the moon. I'm not one of those. I would like to actually have more time with the deep sky, you know. And Paul and Keith laugh at me. Well, we're the moon, you know. But it's okay. We're all good friends. So, in any case, when we're looking at the moon, you know, we don't have the same type of telescope as Paul and Keith do, actually. So, you know, we can show some detail. All right, but we're not going to be able to see the moon in the same way that Paul and Keith see the moon. You know, we just can't do that. And that's okay. Nevertheless, we are the ones that caught the meteor hitting the far side, or the dark side, the part that wasn't lit at that time. And so that's kind of interesting. You know, that was on this side of the moon. We actually caught that during the eclipse. And we could do it again, actually, if we felt like spending all of our time looking at the moon. Then we could actually just sit here and basically increase the brightness here until the side that's unlit on the moon would actually show itself. You know, so I could do it this way. Okay, so you actually see some stars down here, right? Not quite yet. Let me just show you what I mean. If we go this way a little bit, you can see that we have some stars over here. Okay, and meanwhile, we're actually seeing that this side of the moon that's unlit. And if I move it over further, then we can actually see how the glare, okay, will interfere. But once the moon glare leaves us, we can start to see. You see, we can actually see it a little better. But that doesn't give us much to look at. So if we bring it back in, we can just let the glare subside and then just have this to look at. So we actually can see this unlit side. Yeah.
Do Do you know what they call the glow we see on the dark side? It's
Well,
called the Da
Earth.
Vinci glow, after Leonardo da Vinci. He
Oh,
saw
yeah.
it, and he was the first to document it, I guess.
Earthshine, yeah.
Yeah, it's Earth. It's light reflecting from the Earth, shining on the dark side of the moon, and they call it the Da Vinci glow.
Yep, it's part of our cultural backdrop. You know that people have been staring at this thing up in the sky for a long, long time, coming up with theories and ideas as to why it's there, who caused it to be there, and all kinds of things like that. But boy, oh boy, it's really interesting. You know, but yeah. So if it were another meteor to strike the moon, we would actually see a little flash, bing, bing. On here somewhere. But hey, it's okay. We may not. I imagine we won't. But the moon's still up, and of course the telescopes, as you can see, I just have to go and bring those scopes back up. Every now and then I have to basically go play with the settings to bring our telescopes back up, so we get this cam, which is the dome cam looking at the telescope, and then this one, which is riding along with the telescope. Okay, this is the right side of the tube barrel, this is the left side of the tube barrel, and it's aiming straight out of the shutter opening right there. Yep. So I also noticed in terms of getting people to listen tonight, I also noticed that YouTube sometimes has issues, because right now there's 8 people watching us, and by this time we usually have 25 or more. So there must be some event, or YouTube isn't sending out notifications properly. So I'm not sure why that's happening this way. You know what I mean?
Yeah, I guess YouTube's part of Google, and I trust them about as far as I can throw them anymore. Hopefully they didn't hear me say that.
Well, that's probably the reason why we only have 8 people watching, right? But you guys watching, you're the faithful 8. Yep.
You know, I like looking at the moon. My different telescopes. One is a refractor. It's a nice APO refractor. It's great for looking at the moon and the planets, and I love looking at the moon, but the amount of detail is just overwhelming.
Yeah.
I have maybe a half a dozen or so favorite objects or favorite things to look at on the moon. But otherwise, I mean, it's like too much of a good thing.
Yeah.
Can be hard picking stuff out sometimes.
Yep. Now see, Tim says, I didn't get a notification, just saw you're on. That's odd. That's odd. Normally notifications are sent out and people notice that I'm on and they come on. But like I said, it's not going to slow me down. You guys are the faithful 8. You know, check from time to time. So let me just bring us back over a little bit to here.
I haven't received a notification either, for that matter.
I wonder what that's all about.
I don't know.
Wonder why. You know what I could do? I could try stopping the stream and just restarting it to see if that tickles, tickles it to get it to go.
You're the captain of the ship.
Well, I know, but I don't want to drive the Titanic aground here, or into an iceberg. But, all right, you know what? What the heck? There's no such thing as only streaming once. I can stream twice. I can stream more. And, there's a few that are watching. So here's what I'm going to do, guys. I'm going to, because I think the notifications did not go out on YouTube properly, I'm going to hit the stop stream button, and then I'm going to start it back up. So don't go away, because I'm not going to leave. I will be right back, okay? So I'm going to hit stop stream right now. So I'll be back in just a few seconds. Here we go. Okay, so can we tell whether this actually worked? I'm not sure. We are streaming again. we are streaming. And what I'm going to do is I'm going to move the moon a little bit eastward. And now let's go take a look if it actually moves. I couldn't tell if it moved. I think it moved. So I think we're back. Anyway, you guys can tell me if I'm back. I see 13 watching now. Maybe it has to do with that. I'm not sure, you know, why that didn't work right away the last time. For those of you that just joined us, I shut down the stream and restarted it instantly just to see if this would change things. Well, if P and K is on, well then that's pretty interesting too. But people should know, you know, they can pop back and forth with both of us. And I think Keith worked on some programming to make sure that our links would show up. Yes, that's right, Maureen. I never went away, because if you restart the stream within 30 seconds or so, it remains the logical same stream. However, it does cause notifications to change. So possibly the folks got the notification this time. I'm hopeful anyway that they did. We shall see. Okay. Anyway, tonight we're just looking at the moon for a little while. And then we're going to, then we'll figure out what to do, okay? Because I think that there's a lot of other things that we can look at tonight. And as you know, I love the integration of this planetarium software that I've got with our system. All right, so right now we're looking over there at the moon, but if you'll notice, it's on a real angle. There's the horizon. That's because the telescope is tipped way over on its side, trying to look at the sky, and you can see that Betelgeuse is here and Orion is setting. As I mentioned, it was our last gasp of looking at Orion without a moon, and so there's a few things we can look at tonight beyond what we're doing right now. And I would like to start off by heading over to, I want to actually get to Castor and Pollux and go right near Castor and Pollux, which are the Gemini twins. There's this little cluster, and I want to show it to you, and let's go there. Right? This is known as Messier 35. It's a beautiful, beautiful cluster, and it basically it sits there in splendor. It's one of the first clusters that I ever looked at as a kid. When I was looking at the sky. Now you'll notice no stars here because of the fact that I actually have the settings set for looking at the moon. So I need to increase the values, and now you can see as I do that, you can really see that the stars are coming in. And there they are, the beautiful stars. And of course I'm going to blow them away by putting this up here. I know that's what we want. So I can do this, and let's just head eastward. Oh yeah, look at that. Here we go. This is Messier 35, guys. It's a beautiful open cluster in Gemini, and it's a lot of fun to look at. And we'll just take a test photo of it. We'll do, I'm going to do only 6 seconds at 3200 because the moon is right nearby. Now the moon is not very bright, but still, it's bright enough. So let's go check out how 6 seconds at 3200 show us the cluster. Well, there we go. That's pretty, and you can see that cluster. Look at that. Wow, it's just beautiful.
It is. That's nice.
Yeah, it's a really beautiful cluster. I thought 6 seconds would be good, and it was. And of course, this is the moon we took earlier. All right, you can see this is the real size, and then we can zoom in as much as we dare. Okay, that's as far as we go. And you know, like I said, our telescopes are not the telescopes that the P&K folks use, Keith and Paul. I'll be seeing them in a few weeks. Actually, they're going to be coming up. We're going to have fun together. Spending a lot of time at the Pine Bush UFO conference. and it'll be really nice. And I want to say hi to Dee Dee. Welcome, nice to see you. And welcome Dagger Spells. It's good to see you too. Yeah, you guys make us go. You guys make us really, tick. So it's really wonderful that you guys are here. Here we are back again at Measure 35. It's a beautiful open cluster, and if we want to know anything details about it, we can just come to our little wonderful planetarium program. Okay, and now we can see more details. Okay, here's the cluster. It tells you it's an open cluster. All right, it tells you its magnitude. That is to say, brightness. Overall brightness is magnitude 5, so it's quite bright, relatively speaking. And it's actually, as far as its distance, it's 2,772 light years away. Can you believe it? 2,770 light years away. That's a long distance for a cluster. And it's still integral, meaning that the stars are still tied in with each other. Hello, welcome James Dugan from Down Under. And I want to say hi to Marco, who has joined us as well. See, I don't do call-outs every now and then. I do it when I see you guys join. I say hello, because I want to acknowledge that you guys came right away, not make you wait for it. If you came, you deserve the attention. So it's good to see you guys. Hey, Tom, I see you're here too. Tom D. Pretty Moon Views is here. Yes, Tom D. Yeah, Pretty Moon Views. So, how are you doing? And Nancy W's here. Nice to see you. That's good. I think it was the notifications were all whacked out, don't you think, Daryl? I'll bet he does if he got off mute.
You got me. Yeah, it looks like people are trickling in now. Hopefully we'll get a filled audience here shortly.
Oh, I'm sure we will. I'm sure we will. So, we just looked there, and you notice how the planetarium program dims the sky when the moon comes into view. That's sort of an automatic thing that it does, which is kind of clever on the developer's part. They did. That's a really nice feature. I'm probably going to have to figure out another way to look at the night sky here in coming up, because I just want to be able to show us a few other things and look at a few other things. See, this is Castor and Pollux, again, the Gemini twins. Okay, and if you want to know a little more about them, we can show you the mythology. You can actually see the mythological characters of Pollux here and Castor. And they're down at their feet. That's why the foot of Castor, okay, is called the shoe buckle cluster. And the shoe buckle cluster is actually the cluster we just looked at, Measure 35. And that's why it's called the shoe buckle cluster, because that's Castor's shoe. Okay, kind of interesting. And there's another cluster up here in Gemini called NGC 2331. Right, and that's another one that is kind of fun to look at. So we'll check that one out now, and we'll go there. Shall we? Yes, we shall. Here we go. And as we move there, you will see the sky change. The stars go zipping by, and they actually will then show us this cluster. It'll be visible once it should be about here, and then we'll bring it into view a little bit more detail once I do this, and we'll stop it because I know where we are, and then we'll head eastward a little bit, and then stop here. Okay, and now let's do this view. 6 seconds at 3200. Actually, I'll go 8 seconds at 3200 and see what we get. Indeed. Okay, so we'll see this in a sec. And there it is. There's this marvelous little cluster right there. So even on a night like tonight, when the moon is out, we can actually see the cluster. I'll show you something else too that's kind of cool. Let's jump back to this for a sec. Let's make this, let's go up several stops from 4,000 to 5,000 to 6,400 and take a picture at 8 seconds again. So 3 stops, meaning 3 camera stops is what we've increased it to. All right. And as we look at that, okay, you'll notice now our noise reduction kicks in. You see the noise being reduced around the screen. But you can see this beautiful cluster now, and you can see there's actually more members of the cluster hidden within here that we didn't actually see. Now the thing is that's interesting about these clusters is that many of the stars we see here are all part of the same family, all born at the same time, once in a cloud of gas, just like the Orion Nebula. But over time they've moved and stuck together. The gas and dust has been dispersed, usually by the stellar winds from these young stars when they're young and hot. And so that explains why we don't often see that these open clusters have a tremendous amount of gas and dust around them. Some have dust, but many of them have migrated away, and you think, wow, they're just born out in open space. No, they're not. They're born in these stellar nurseries too, but we don't see it that way because the universe has a long history, and the stars were born a long time ago, so we can actually, there's time for this dust and gas to disperse, which is kind of interesting there, you know. Hey, Ted Bronson, welcome. DW, welcome. Good to see you guys. Amal, nice to see you. Thanks for coming in. D. Smith, good to see you too. So now this view here then of this cluster, this little tiny cluster, is up here in Gemini, okay? And this is Gemini right here, and we're looking at this little tiny cluster, and the moon, don't forget, is right there. So we're right near the moon right now, but as we keep moving, we're going to try and find our way to a few other places to check it out. Like here's one called the Twinkling Comet Cluster, otherwise known as NGC 2420. And I'm with you, Daryl. Daryl said this before, folks. Who knows how they came up with these names? I'd like to find out who it was that came up with these names, because that's kind of silly, you know?
Yeah.
You know? So I'm going to only put the constellation lines in just so we have a rough gauge. Okay? But this basically tells us this is actually a little tiny cluster, and it's a very rich cluster. It has more than 100 stars. So let's check it out. Let's go over there and let's go see what this little gem looks like. So here we go. We're on our way. And there we are. We're getting there. You can start to see a couple of things. Hey, Ted. Thank you so much, man. Ah, Ted. That's great, Ted. You know, that's what I like about you guys. You know, you actually back up what you say sometimes with something like this that really, you know, makes it all worth it for me. And I'm actually going to give all of you props tomorrow. Actually, Saturday when I do my talk. I'll be in front of an audience of about 600 to 800, and I'm going to mention the folks in. Oh, DW, thanks, man. I'm going to mention to the folks there that I probably have the greatest audience for a live stream in existence. You guys are faithful. You come to me all the time, and I'm really, really happy that you do. And I want everybody to know that I really appreciate you. So you'll see. You'll hear about it, because there'll be fallout from me saying this. I'm sure. In a good way. In a good way. All right, let's take a look at the Twinkling Comet Cluster. We'll do 8 seconds at 6,400. We're a little further away from the moon, and we'll see what we get. Now, this is, again, in Gemini. We're kind of looking at this little cluster that's up here in Gemini. And these little white red lines I just put in show what are called isophotes. They're the borders for the constellations. And so this little cluster happens to just be within Gemini over here. Okay? And we're going to look at this next, Daryl. But let's go back and check out what we got here. Let's go take a look at this. There it is. Look at that little cluster. That is so amazing. It's a beautiful little cluster. And you can see that there's actually quite a number of stars, but you'll notice they're really kind of dim, aren't they? Amal, thank you so much. Holy cow. Wow, you guys are amazing.
That's crazy. You guys are too much. Thank you on Mark's behalf.
Well, yeah, you have to understand, and then they're right too. When they can, I don't expect anyone to donate a thing. I really don't. I never expected that going in. I didn't even know I had that capability to have that happen for the longest time. But what it does for me is it helps me maintain the observatory. And that's just, to me, by far the best thing that could ever happen. I get to continue to do this. I don't use this money frivolously. It goes to getting me the equipment I need to modify the observatory, to make it better for all of you. Amal, there's no fee. It's free, man. You choose to do that, and I humbly appreciate your attendance. That's just very kind. But look at that beautiful cluster, huh? And it's probably some distance away because the stars are actually very compact. And the fact that the stars are so compact shows that the cluster formed at some distance, and they probably formed near each other just like other clusters. And then they migrate away slowly. So it's interesting to see this, all right? And actually, to bring this up, James brings up something. I'm just going to go to this really fast here. This is the black hole that we saw today. Daryl and I and Amanda, we actually spent time discussing this for 2 hours and 10 minutes. And it's actually going to be the source for SkyTour Radio on Sunday. I will be in the air on Sunday on the way back here from Arkansas after delivering my talk on Saturday. And this black hole hits every single this hits every single every single facet of Einstein's theory of relativity. Everything we see here was predicted by relativity the whole way. We saw Dee Dee, my gosh, man, guys, you're making me blush over here, guys. And it's not just the orange light here hitting me in the face. I'm humbled. Thank you, Dee Dee. You're a sweetheart. You've always been. You ever want to come on the air with us? Let me know. You're welcome to come on. As anyone else is. I'm always happy to have people come on when we have a moment to do that. So this black hole, you notice this bright area here? This is photons of light that is speeding toward us, coming toward us. And this is an area that's going away from us. All right, so we're actually seeing Doppler shifted light here. Higher energy light here, which in the visual spectrum would be blue to us. And this would be redder to us. Now, I know it's red, but this is the way radio... this is radio waves out here. So radio waves don't have a quote-unquote color. They're all in the red, right? So that's why they choose an orangey color, for showing these things. But, nevertheless, this circular donut here, this is the key item here. This is actually the location where space is warped so much that the photons that are circling this event horizon at the black hole actually end up circling around amongst themselves here and can't get out anymore. And that has not to do with the fact that gravity is tugging on them too tightly. Photons don't have mass. So what is it? It's the warping of space that gravity does. It warps the very fabric of space. And the photons, as I said before, follow the fabric of space. So as they follow the fabric of space, guess what? If there's a warp, they're going to follow the warp. All right? To them, they're going straight, but they're following the warpage. And because of that, we see them being bent by gravity and say, oh, look, they're being bent by gravity. Does that mean they have mass? No, they don't have mass. Not in the classical sense. But we can treat them as if they do, based on the gravity and how much the warpage of space affects them. All right? And that's what we see here. So this here is a place where the photons, the ones here, have just as likely a chance to come out and reach us as getting sucked in and spiraling into this black hole. And when I say sucked in, I don't mean pulled in by gravity. I mean like a whirlpool. They would circle tighter and tighter and tighter until they enter this zone from which they're now circling endlessly within and orbiting within this location. This location, defined by Schwarzschild, is the Schwarzschild radius, this size, and that Schwarzschild radius is defined by the mass of what's in this black hole. Okay, and that radius, beyond which a photon goes, it can no longer escape from the black hole. Right above this, they can likely escape or not escape and get and spiral back in. So the chances are 50-50, for instance, that they can get out. Out here, it's a little better, but once they get this close, they're just as likely to get pulled in as possibly escape. And that's why we hear about that. And again, they don't have mass. Gravity's not pulling on them. Gravity is causing a warpage in the fabric of space. I know those words sound foreign to a lot of you, and I don't blame you. It is foreign. But when we talk about black holes, you just have to kind of accept that foreign terms are going to happen now and then. If you consider a sheet pulled taut at all four corners and you toss a bowling ball into the middle of it, what happens? Well, the bowling ball makes a depression in the center. And if you take a marble and just let go of it at the edge of the sheet, it's going to roll right in and bop into the bowling ball, right? Okay. Well, if that marble is a photon and the bowling ball is the black hole, what if you actually give the photon some momentum, and that is to shoot it in a direction not toward the bowling ball, but around the bowling ball? Well, what happens? It may orbit the bowling ball a few times. Okay. However, unlike the bowling ball analogy, photon energies can be enhanced or detracted based on what they interact with. So if we see that these photons, which are massless, follow the gravity of the warp, if that warp gets so deep that the photons begin to spiral toward this area right here, then they could spiral into it, and thus they will never get out. All right. So, because their energy doesn't change, their energy actually is affected by the black hole, but it's not like the black hole is pulling them in. They are following space. That's all. So it's kind of an interesting dilemma. It's actually something. This is in my presentation for Arkansas. I have a lot to talk about with this on Saturday afternoon down there. So they should be hundreds of people in the audience that are going to be eager to hear about this. So we'll see what happens. I'm really excited about it. But anyway, back to the matters at hand. We have a universe to see. Now, this is that little tiny wonderful cluster. It's got about 100 stars in it. It's just beautiful. And we talked about the fact that the clusters form. They're pretty much the same size overall. Hey, Justin T, welcome. And the fact is, we want to find out whether these clusters are, how far away they are and so forth. And these are clusters that no one ever thinks about and doesn't ever see. But, they're really cool. And now we're going to look at a little nebula that I really like. It's called the Eskimo Nebula. You've seen the Eskimo, haven't you, Daryl? Daryl's on mute. He'll unmute in a sec.
Yes, I'm sorry. Yes, I've seen the Eskimo. One rare night, I saw the Eskimo at about 800 power through a 13-inch telescope, and
wow.
It looked just like the photographs.
Wow.
800 power is a really rare thing here with the turbulent air we generally get in Colorado.
Yeah.
But it was spectacular to see, and it looked very much just like the photos of it do.
Very cool.
Looked like an Eskimo with fur around his head.
Mm-hmm. Let's do this. Let's. Now, we do have the moon, so we'll do 15 seconds at 8,000. So it's not that far away from the moon, but the moon is setting, as is Gemini. So let's try and catch this before it sets. The sky will be a little bit bright, and the Eskimo is a little bit low surface brightness. But we will see if it can show up. Anyway, why not, right? All right.
Yeah, Amal. Mark, Amal's asking a question. How can we listen to your presentation? Or didn't you say you're going to stream it or try to?
Nah, that's gonna be Pine Bush. I'm not in control of whether we can stream the presentation down there. Unfortunately. Yeah, I don't see the Eskimo right now. Do you see it?
Not offhand.
It would be kind of off to the left here.
The Eskimo is a planetary, if I remember correctly.
Yeah, so I was looking for that color.
It may not have much surface brightness.
I was looking for the blue color that's characteristic. You know what it could be? Let me just check something here. Make sure that... I don't know if I actually... I wonder if the telescope actually got over to it. It had to do... It had to. It may not have, though. Let me just make sure. Okay, I'm going to hit that again. I'm going to see if we're getting there. See if anything changes. Oh, yeah. Okay, folks. My mistake. I was a dummy. I said, let's go look at the Eskimo, and then didn't bother to go see it.
There you go. Happens to the best of us.
Yeah, and mostly to me anyway, you know. So I'm glad that you guys finally got the alerts that we're streaming. So I had to stop and start the stream again to kick the alerts at YouTube's side, because I don't know why they weren't showing up. But I did that so that you guys could know that we're doing this. Because I know you like this stuff. We all do. We all like this. Okay. 15 seconds at 8,000 again, but this time, let me actually go into a 4K video for a second. Okay, excuse me.
The telescope I saw the Eskimo through that one time, that was the nastiest looking old homemade thing you ever saw. The guy, it had originally been an old Coulter tube Dobsonian.
Oh yeah.
And he wound up building a wooden box on the bottom to hold the primary, and built a wooden secondary, and the struts on the telescope were wood also.
Wow.
But boy, that thing performed. It was quite a decent telescope.
That's excellent. There it is. It's right there. So I'm going to move us over a little bit more, and then we'll image it now in full. First, we're going to shut off the 4K mode, and we're going to drop. The exposure is going to be 15 seconds, and I'm going to go 12,800 just to see what happens. Let us go see. Alright, so the planetary nebulas have this really characteristic and beautiful blue color, which Amanda really likes. So I'm sorry she isn't here to see this, okay? But she said she would be part of the stream tonight, but she may have gotten sidetracked, possibly fell asleep. She doesn't get a lot of sleep, guys, so we got to be gentle with her. You see that there? There it is. Now,
oh yeah.
It doesn't take a lot to capture some of these planetaries, but some of them have these faint, wispy structures, and this one just walked a little bit. You can see this not quite perfect. From back here, it looks like it's perfect, but what we do is we zoom in on the stars to see if they're dots or if they're elongated, and they're elongated. So this is not a good photograph, not one that would pass my muster if we were going to be taking a photo of the night sky. And what I'm going to do is I'm going to bring us a little bit westward, like this, and then drop it down a little bit, like that. Okay, and now I'm going to drop the exposure level down to 8,000. And do this, and we'll do 8,000 at 15 seconds. The sensitivity, the higher the number goes, the more noise we get in our view. And I say noise, that's digital noise that's generated, and that has to do with the fact that we're pushing the processor, pushing the sensor quite a bit in order to get what we get. So we don't want to do that if we don't have to. So let's see. Here we are. We have our image here. Let's go into our mode here, and maybe that's a little bit of processing there. That's too much for planetary. And the stars walked just a little bit. However, we can definitely see, and once we get a good shot, you can actually definitely see the little Eskimo, shape there. Do you see it? That inner shape right there? There it is. And the star's a little bit elongated, so we're going to take another photo to get this even better.
Yeah.
Yeah.
And that blue fringe around the edges, that makes the fur on
That's
the
right.
Eskimo's hood.
That's right. Okay, now we're going to do 10 seconds at 8,000 and to close in on a better exposure to try and show the delicacy of that fringe and the inner area. And since I worked on getting the mirrors properly aligned to each other, the images are 1,000% better, I think.
Oh yeah.
So, oh, look at that. See that now?
Yep.
Now you can see that. And of course, this is the noise you see out here. And we'll work on this to try and get this even better than that. Okay, so look at that. That is really pretty.
And the white dwarf in the center makes his nose.
That's right.
That's a nice picture, Mark.
Yeah, that's the process shot. Yep.
No.
Now I can alter that a little bit, and I think I will just bring up the brightness just a little bit, just to kind of give us a little bit of a view that makes a little more sense here. Yeah, isn't that pretty? You can actually see the multiple facets of this nebula. It's got this outer shell, and this shell is probably a spherical shell of the star, that actually pushed off its outer envelope. And this color is caused by oxygen atoms in the cloud, in this gas, that are being ionized by this white dwarf in the middle here. Now, if you think that the white dwarf is this big, it's not. The star image is just that big because it's bloated by our atmosphere. If we were out in space, the central star would be smaller than any point you can see in this image here. Actually, smaller than any point anywhere on here, because all these star images are bloated, even the smallest ones, because stars are only ever point sources. So that means that it gives you an idea basically of how bright stars are and how powerful their energies are. That's a beautiful shot. If anyone wants that, it'll be up on the SkyTour LiveStream page. And Maureen just said an error occurred. I saw that with the SpaceX launch today. A number of errors had occurred. It's not us, it's YouTube, just so you know. So just refresh and it comes back. So thank you, Maureen, for pointing that out. And let's do this. Let's go back to this again, and let's just get rid of that. And now I want to do this. I'm gonna, again, closing in on a better shot. I'm gonna do this. I'm gonna reduce the ISO by 3 stops and increase this by 5 seconds. Okay, and now let's take a better shot. Now, by reducing the ISO, we're going to get less noise in the result. And when we go back to our results that we did see, okay, here's the results. All right, and when we look, all right, let me zoom in and you'll see it. When the new one comes in, you'll see it overlay this, and you'll watch the difference in this noise. Ready? So it'll be done in a sec. Okay, well, okay, you can see the difference, but obviously we had a little bit of a walking issue there. So hardly one to write home about. So what I'll do is go back right away and just take another shot, and let's go back and wait for it. So anyway, this is what we saw, and you can see the noise algorithm processing out the noise. So as we come in again, that's a gorgeous little shot. You can see that inner shell. This shows that there were several events to puff off the outer layers of this star. Oh, that's
There's quite a bit of texture in that outer fringe area too.
Yeah, and I'm wondering whether some of that's due to the noise. See this though? This is
I've seen it in several different exposures you've shot.
Yeah.
It's really there.
Yeah. No, I think that the coarse texture is. You're right. Look at this, huh? Oh, there's another thing too. You notice this right here. There's something there. There's some stuff here.
And that one there at 8 o'clock, that kind of dark feature.
Yeah, right
like
there.
A point. Yep.
Yep.
That's real.
Yep. This is beautiful. So we're closing in on the right exposure for this nebula. And let's just do one more thing. Let's try and get rid of even more noise. Let's go down to 2,500. No, I'm even going to risk going to 2,000. And I'll say 20 seconds. And let's see what we get. So we actually are going to get slightly dimmer, but we should get a better result. All right. And this is cool. I mean, I'm really enjoying this. This is the real world. This is how we actually close in on getting our our shots right. Is we actually do these repeat exposures. So now I've gone down several more stops, and this noise will get even more reduced if we don't walk. Looks like we walked a little bit, but notice how the noise is reduced even more. So this is really pretty too. And it's what I really want you to point. What I want to point out to you guys is, oh, look at that. Is that Daryl? Do you know? I mean, I don't remember.
Great.
You see this rim all the way around the outside edge?
Yep.
Is that a real thing on the Eskimo? I haven't looked.
I think it is. Yeah. They're up around 10 to 2 o'clock. I mean, it looks kind of rough on the edges.
Yeah, yeah.
I see some modeling.
Yeah, that me too.
Like turbulence or clouds, and you can still see that dark kind of triangle shape at 8 o'clock.
Yeah, right here.
And then at about 7 to 4 or 5 o'clock,
yeah,
underneath the second ring, you can see another dark feature.
Yeah.
I think you got real stuff there.
Yeah, I think we have to take a look at the other imagery online to see if this is real. But that's beautiful. I think we're kind of closed in on it. And since it's still so bright, I'm actually going to do one more where I actually reduce by 3 more stops the noise. 1, 2, 3. So now it's at 1,000 for 20 seconds. And so that's 3 more stops. So it's going to be dimmer overall, but let's see what happens. Hello, Ronald. Good to hear from you. Ronald is here. Ronald graciously allowed Amanda to usurp his station today so that Daryl and I and Amanda could talk about the black hole. Yeah, it was really good.
I am about to post a link in chat, Mark, for Wiki's Eskimo Nebula page.
Okay.
And if you can look at it, the image at the upper left, it looks remarkably like what you have been taking pictures of.
Okay.
It's the small blue one. Let me find the right page here. Here it comes, people. You'll have to open the link. Look for the image, the blue image at the upper left of the article. It looks remarkably like that.
Okay.
And then the famous, I think it's a Hubble image, is over on the right side. It's kind of yellows and stuff, probably in that Hubble palette.
Right.
And that shows a great detail in it. But I think you get a good feeling for the face and the nebula and the fur around his head, all that.
There we go. Look at this. Now this is probably the best one so far then. Because this, if you look at this, we can actually see a lot of detail that doesn't elude us. And you see there's a dark area just out around the star, then there's a first ring, actually sphere, and then a second one on the outside. That's pretty nice. Let's see if we can process, if any processing will help that along. First of all, let's get rid of this. All right. Wow. So that's pretty much the same. So let me let's see what we can get here if we go in here. How about? All right, let's do this. Let's do a little processing now on this. Okay, a little processing here. Well, here's, if we want to just show the inner shell. I can show the inner shell. You can actually see a lot of detail in that inner shell here. You see that? See that, Daryl?
I do, yeah. I got too many windows open here.
Yeah, in this inner shell now, when I change some of the settings, you can actually see a lot of really interesting detail and modeling in there. Right. And then if I bring this back the other way, you can see the outer shell here pretty clearly. I also see a little artifact right there, which seems to be a real object right here. You see that?
Uh-huh.
I'm not sure what that is.
You're catching real stuff there.
That's pretty cool.
If you could see that picture from Wikipedia, it's an exposure taken through a 32-inch telescope compared to a 10-inch in your case. But you're catching an impressive amount of detail there compared to the one from the big telescope.
All right, I'm going to check it out. Okay. Let's go see. Oh, yeah. You're right. That's pretty cool. Very cool. It's just brighter. It's not any more detailed. You know?
Yeah.
Wow,
but
that's beautiful.
A lot of the fringe on the outside there, the details and the modeling and that, and it's all, you're catching it, man.
Very, very cool.
I don't remember you ever showing us this before. I'm glad you did.
Yeah, I don't remember actually showing it either. I think that maybe we overlooked it in the past. But, you know, here it is. This is a beautiful, beautiful nebula. And, you know, you can't see it unless you maintain your telescopes. Because there's a lot of fine detail that get lost if you didn't do this. And you can actually see some really interesting lights and darks in here. And that's really there. I just confirmed. Go to that link Daryl supplied and you can actually see it. You know,
Amanda's going to wish she'd seen this. She likes planetary. She loves that color.
Yeah.
And she loves the cat's eye, of course. I think this is cooler looking than the cat's eye myself.
Oh, well, me too, actually. I mean, we've looked at the cat's eye, and this is, it might be the cat's meow for Amanda, but this is more like the cat's purr, paw, and meow, okay?
There you go.
Indeed. Well, Ronald's asking a question, why the variance in the layers? That's actually a pretty well-understood phenomenon that I'll tell you about. As stars begin to use up all their hydrogen, what happens is they begin to fuse other elements. So when the hydrogen's exhausted, then the star begins to shrink because the outer radiation pressure is now less than the gravity trying to crush the star. Because always the star is in equilibrium. It's outputting as much energy as it takes to hold itself up. Okay, it's in equilibrium. But if that changes, if the output wanes a little bit because the source fuel is being used up, it'll contract. The star gets smaller. And as it gets smaller, it gets hotter. And two things happen. First of all, the core gets hotter of the star because now the gravity is pushing that same amount of mass into a smaller space, for one thing. The next thing that happens is, as that stuff ends up getting brought in from the outside part of the star, as that star contracts, some of that hydrogen that's in the outer envelope of the star that was on the outside that never was in fusion before, because only the core is fusing. The outer is very hot, it's plasma, but it wasn't fusing. Well, as that outer envelope gets drawn closer to the core, then sometimes a small shell of hydrogen can begin fusing all over again to make helium. And now in the core you might get helium converting to carbon and being fused into carbon. So what happens is this causes the star to now have a renewed fusion and it bloats up into a much larger red giant. So the star would then go much bigger, and then as the fuels fluctuate in the core of the star and the outer shells of the star where it's fusing other materials, then what happens is the outer layers pulsate. And sometimes the star gets so big as a red giant that the outer layers are no longer gravitationally bound as strongly as the inner layers. And it doesn't take much radiation pressure to cause those objects to actually, or that gas in the outer layer to actually begin to migrate away from the star. The renewed radiation pressure from inside can push that other stuff away because the balance of the forces ends up being such that it's easier to push it away than gravity pulling it back in. So that happens too. And that's what these are. These are puffed off shells of gas from the outer layers of the star, which is pretty cool. And this inner layer here shows that a second event had occurred where another layer got puffed off. So this thing varied like at least twice, maybe more. And it went poof, and it poofed this all off, and then poof, it poofed this all off earlier, or later rather, in its history. The inner star here in the middle is white because it's a white dwarf. It's the end state of life for a normal hydrogen-fusing dwarf, which is what our sun is. If you can call an 865,000-mile diameter star a dwarf. And it doesn't mean it's tiny. It just has to be. It just means that it's a normal hydrogen-fusing star. Normal stars. Well, anyway.
You might say not a giant.
Yeah, that's true. That's right. Because giant stars are different parts of evolution which isn't conducive to life. And giant stars at the left end of the star diagram we call the Hertzsprung-Russell diagram. Stars back there are hot and white, like the Belt of Orion stars, for instance, or hot and blue rather, and they're very, very hot, and they have so much ultraviolet radiation that sometimes the majority of the radiation they give off is in the ultraviolet spectrum, and still they're exceedingly bright in the visual spectrum. So that kind of gives you an idea. So a star like this became a red giant. And then as the fuels waned and the star's mass was sloughed off like this, then what happened was the star began to contract. And it just kept going. And finally, with no more fusion products, it contracted to the point where the star's outer layers were literally completely blown off the star, like you see here. But as it contracted, it got a lot hotter. And what it ended up being in the center is an area where the atoms were no longer, or couldn't even be unified as a proton, electrons, and so forth. They're actually just protons, separate protons, electrons, and so on. And so what happened is the electrons themselves are packed into every single layer in the atom. At this stage, and what that means is that you can't compress them anymore. They actually push back with a pressure all their own, and that's called electron degeneracy pressure. And that pressure prevents the star from collapsing further. So that has to do with the mass of the original star. And if that star was below, and here's the magic number, 1.44 solar masses, then it could only ever become a white dwarf. And that's a limit that on white dwarfs that was found by Subrahmanyam Chandrasekhar. And Chandrasekhar found that number was that magic dividing line between whether a star would remain a white dwarf or collapse further into the really, really odd neutron star. And that's a whole nother discussion of stellar evolution. But that's interesting because the white dwarfs are the end state of most of the stars on what we call the main sequence, that are between A to the F to G, K, and M. Okay, and the farther down that scale you go, the stars live longer, and of course last longer. So what I really mean, they don't live at all, but they last longer, and they can be more stable or less stable depending on the point in their own evolution. But either way, these stars end up sloughing off their outer layers, these normal stars like our sun, and make these beautiful nebulae. And that white dwarf is so hot at that time, and they're so hot, there's no fusion occurring anymore in this star, in this remnant, I should say. But it's giving off such high energy radiation because it contracted so far that it's in the ultraviolet it gives it off. And that ultraviolet energy ionizes the oxygen that's in this particular envelope, right? The hydrogen is no longer here. The hydrogen was probably used up, or it went out beyond the exterior here. But the hydrogen isn't there, but the oxygen is. And the oxygen is doubly ionized, so 2 electrons get pushed off the atom. But when they recombine and come back in, they go to particular locations on the atom when they come back in this cloud. And that's called recombination. And when they do that, the majority of the atoms go to a particular location, and the electrons, go to a particular location in the oxygen atom, energy level, and that gives off this characteristic blue light we see. There's certainly other levels that they get to, but this is the one that's predominant, and that's why planetary nebula always seem to show up with a little bit of blue. Remember the dumbbell? We have a beautiful image of the dumbbell. It's about this big on the screen, compared to this nebula. I don't even know if they give the distance to this nebula. Let's go see, shall we? Yeah, they say it's about 4,100 light years. Can you believe it? So yeah, this is 4,100 light years away, the Eskimo nebula. And it's just a really lovely nebula. So there it is for all of us to see with all of its detail. And it would pass as a little blue star, kind of like Neptune. Maybe it looked to people, which is why they were called planetary nebulae, because the label was given because they were not to be mistaken as planets. All right, so that's how that works. But we've spent a lot of time on this little planetary, but boy, is it beautiful, isn't it?
It is.
Yeah.
Mark, a question. What is the actual size range for the white dwarf?
Oh, the white dwarf could be about Earth-sized. Okay, now that's a star that's, say the sun size or even larger, up to 1.44 solar masses, and it can be down to about the Earth size, maybe a little bigger. And that's about the size for an electron degenerate surface in the white dwarf, where the electrons will end up being the thing that keeps the star stable. They're very dense. Okay, they're very dense, but neutron stars are even more dense.
Oh, yeah.
And neutron stars are even smaller. Neutron stars go now from the size of the Earth down to the size of like Manhattan Island.
Right.
Which is crazy.
I've heard that said a lot.
Yeah.
Well, great job, man. I think that's really beautiful.
Me too. I'm surprised at how pretty it is, but
Uh-huh. I'll save it for future reference, man.
Oh, I'm gonna
go back and look at that again. Probably this fall or next winter at this point, but hopefully we'll go back and see it again.
Well, the other thing I can do, is actually take a whole bunch of images of it and then stack them. It doesn't matter if it's a bright object. Don't forget. We can actually get a lot of the detail that we're only seeing in this one shot. We can get a lot more detail by doing that. But let's continue on our merry way here, because I'd like to get folks to check out some of the other things that we're looking at as well. And let's see if we can. I was checking to see if we can get up there now, and it looks like we might be able to. I don't know. Well, we're gonna try it. Let's go see if we can see this little guy right here. It's not such a little guy after all. It's a globular cluster, and it's actually it's actually called it's C25 or NGC 2419 is its designation. But let's go see if we can check it out, because I'm really excited to see if we can get up there. So the telescope is moving. Alright, and I want to check out whether we're getting to it or not. Okay, and let's do this. Alright. Okay, so far so good. It looks like that's where we are. And let's go a little to the east here. Okay, and jog us. Alright. Okay, let's do 15 seconds at, let's say 15 seconds to 2000. Alright, and let's go. Telescope is stable. We should be okay. Ex-Sapper Bad Man, you've been here for a while. I didn't say hi to you. Glad you're here. Thanks for coming along. And hey there, most intelligent ever born. That's a great name. Good to see you. And let's see here. How about turning off the? Let's turn off this. Let me see the viewer here. I'm wondering if I'm getting artifacts from the dome. Is my dome in the way? Because I did. Okay, I probably need to do a little longer. Let's just do that. Okay, so we come back here, and now let's go back and let's say 15 seconds at 8,000. I was turning it way down. We'll do, okay, 15 seconds at 10,000. Here we go. Now we'll go.
I thought I saw a faint fuzzy in the last image. Maybe it'll come up now.
Well, it will. See, I had it at only 2,000, so it was like 2,000 sensitivity. I mean, we take pictures on far more than that on a typical basis. Yeah, Dee's a sniper, man. She's great. There it is. See it right there?
Uh-huh.
That is our intergalactic wanderer. It's a globular cluster that's pretty far away. If we close in, see, it's really faint.
Yep.
But still, it looks pretty nice. And let's, yeah, see, we want to actually, if I had a little processing, let's do a little processing here to show you this thing a little better. Okay, a little more processing here. And I'm going to take off that. Alright, so we'll leave it at that for now, and then I will come back and do this. Now we'll do 12,000. Oops, that's the wrong way. 12,800 for 15 seconds. Okay, no, 20 seconds. There we go. I'm also getting to the point, guys, where I'm going to be realigning the telescope and getting it all perfectly aligned again. Oops, I went 30 seconds. Okay, well, we'll see what happens. Telescope can handle 30 seconds, but if there's a slight wind throughout that 30 seconds or in that 30 seconds, it can ruin the view. You know, so you run the chance of, the longer the exposure, you run the chance of ruining it with some shake. And I have a dew cap on the telescope, meaning there's an extension off the barrel, and that kind of acts like this came out good. It kind of acts like a wind catcher. Here you go. You can actually see it. See that? Pretty cool.
Can almost see stars now.
Yep. I mean, it's
the cluster, that is.
Yeah, you're absolutely right. And there's a tiniest bit of walk here, and if we zoom in on the stars, you can see that they're a little bit elongated. There was clearly a bump, probably caused by a little gust that went sailing through the dome. you know, but not bad, not bad. All right, and so this is now this guy, and let's see if this makes a difference. Oh yeah, you can still see some stars there. Look at that.
Yeah,
they're faint.
Kind of a granular look to it.
Mm-hmm. And I'm sure we could, we could acquire the stars if we wanted to. But let's go back to our view here. Actually, I'm going to go to our planetarium view and find the next object up for bids on The Price is Right. Yeah. Yeah, and see, getting away from the moon is a good idea, for sure. And if any of you know the night sky and you're interested in seeing something, let me know.
There's the Beehive right there.
You know, I saw that, and I'm thinking I'll go to the Beehive shortly. I just want to... we went to this planetary a few minutes ago. That's the one we saw. That was the... it's also known as the Clown Face Nebula. Did you know that? Yeah, NGC 2392, actually. Yeah. The Clown Face Nebula.
Oh, right.
Yeah.
The Eskimo.
Yeah. All right, so let's go here. Let's go check out NGC 2395, another gem in the sky. And we're going to go there now. So we are moving on our way to it. You can see the stars zipping by. Those aren't comets. Those are the stars. And telescope is getting its final alignment right here. There it goes. As you see, it's moving. And as I said, I will be realigning the telescope when the weather gets just a little bit warmer, so that the object we want to see will always be in the middle. And this is in preparation for getting another instrument that we're going to put out in the observatory that's going to be a little bit more powerful and a little bit more more powerful. Let's put it that way. I'm going to be getting...
a secret?
Not really. I'm just trying to, first of all, saying anything yet, because I don't know which way I'm going to go. Whether I'm going to go with the professional meat or the professional celestron. There's two ways I want to go, and I'm not sure which way it's going to be. It's just I'm not being cagey. I'm just being unwilling to make a decision. Basically, it's me.
I hear you.
Yeah.
I vote Celestron.
Mm-hmm.
That's just me. I've owned both, and Celestron has better customer service.
Yeah, that's for sure. I might get one of the HDs, which is a better telescope.
I almost bought one of the HDs a while back. I'm still kind of on the fence about one.
Okay.
I discovered doing some research that of the different HDs, there's an 8-inch, the 9.25-inch, and the 11-inch. The design of each of those telescopes is somewhat different than the others.
Okay.
And because of the turbulence in the air here in Colorado, well, I prefer to run at a lower F ratio if possible.
Mm-hmm.
They do make focal reducers for the 8-inch and the 11-inch,
Mm-hmm.
but they told me that they do not for the 9 1/4 because of its different optical design. There is an optical element right at the tailpiece of the telescope, and evidently they can't configure a focal reducer to work with it.
Right.
The focal reducers for the 8 and the 11, you're in a whole different league than you are with the regular Celestron Schmidt Cassegrains.
Yep.
The focal reducers and everything on those HD telescopes, all the accessories are really expensive compared to those of the regular Schmidt Casses.
Sure.
But they sure are nice. They sure are nice telescopes.
Oh yeah, they have to be, they have to be really beautiful telescopes, So there's that little tiny cluster that I was telling you about. Standing out there in the crowd all by itself, and it's amazing because when you look at these, it's like you're looking at the light that's come thousands of light years to us, and no one's seeing it except us. So, I mean, I always feel honored when I look at stuff in the sky for that reason. It's kind of a silly thing, I know. But, you know, that's kind of how I am. You know, who's there to see it, you know, except me. And now all of you. So let's just move over a little bit now. See, we got a few other things too down here, but these, if we look carefully here, you'll notice there's settings. See that? If we wanted to look where we weren't setting, okay, that's like over here. And what's over here? Well, we have these constellations over here.
Crater the Cup.
Yep. We've got Crater.
Down below Virgo.
Yep. Right, and Virgo is just above here, where all these wonderful galaxies are. This is Leo over here. Virgo's over here. And M87. We should take a look at M87 again tonight, don't you think? Because we just saw it today in a whole new light, so to speak.
Absolutely.
Yeah, so we'll do that. But we'll have to move the dome to get us into that configuration. But let's go see how far I can go. And I will do that. But first things first. The first thing I want to do is bring us down, if I can get there, without having to move too much. I want to actually show us this cluster up here, which you mentioned before, the Beehive. The Beehive cluster is also known as Persepi, or M44, Messier 44. And the Beehive is a beautiful cluster. I looked at it many times as a kid. And it just has such a beautiful collection of stars that are just very enjoyable to look at. And they are wonderfully bright. You know, and as a kid with a 2.4-inch refractor, which was my claim to fame, and that means 2.4 inches in diameter was the lens objective size. That was my favorite telescope. You know why? Because it was my only telescope, and my parents couldn't afford a telescope for me. And when I was 9, I had surgery, and after that surgery, I basically had to sit at home. I couldn't do anything, so my parents figured that they'll spend what little money they had, and they also got donations from friends too, and they bought me a telescope, and it was a 2.4-inch diameter objective lens, and it was made by the company called Scope. You remember them? And
no, I don't. I remember Tasco.
Yeah, Tasco was another one, but this was Scope, and it came with a astronomy book that told you all about the night sky, and I studied that thing like it was a journal, and I really enjoyed it. I'm going to take a 20-second photo at 12,800 to find all the faint stars in Persepi. Okay, and I got to tell you, when I studied it and studied this book, I learned a lot about astronomy, you know, and I studied it so much, and I looked at it so thoroughly and so completely that I basically broke the binding, and pieces of the book were coming apart in my hands off the binding. So I taped them back into the binding, and the book became like it was like taped everywhere, and it was amazing because the book served its purpose, and I actually really enjoyed it. And then it was lost to time because segments of the book got lost or fell away, and I couldn't find them anymore. Went to school, little pieces of that book disappeared. You know, the dog ate one, I remember. So, you know, things like that happen. But that really was the most enduring book for me. And it had on the cover, it had a red circle with stars in it that were white, and that was a particular shot taken in a certain kind of light. I didn't understand it at the time, but it was the coolest shot I ever saw, and I said I want to take pictures like that someday. And look, guys, here I am. I'm doing it. I'm taking these pictures of star clusters that are far, far away, and showing you planetary nebulae and galaxies that are far, far away. and I am absolutely just loving it, you know. And I'm doing it from inside the warmth of my office. Well, the relative warmth. I mean, it is a little bit chilly in here sometimes, but I have to tell you, this makes it all worth it. And then to see this list of you guys sitting out here, you know, listening, oh man, I just love it so much. You know, there's 27 of you here with me right now tonight. A very good assortment, a good healthy supply of folks that want to see the astronomical world. And I appreciate you very much. Now, this is Praesepe, so we now notice that there's a bunch of stars here. They're all pretty much the same type based on the fact that they all formed at the same time. But I want to do something now that might be something worthwhile, and that is I'm going to bring up my telescope control cluster. Okay, and we're going to turn off the tracking. I'm going to go toward the west a little bit first. Okay, and now we're going to turn off tracking, and that means turn the telescope track off, so now you'll see that the stars are going to move. And as I've told you before, that's the Earth rotating out from under the stars in real time. Okay, and then we're going to just take a photo. We'll do 20 seconds, and I want you to see the star trails that are generated by this. And these star trails that you're going to see, and it freezes when it takes a picture like that, so just understand that's why it stopped. These star trails are going to help us see the colors of the stars, because they're not all identically the same. Some are slightly different based on their mass and their initial formation, but they're generally close. And you'll notice that you'll see most of these stars are about the same. See, in Praesepe, some stars that may look decidedly or markedly different colors could very well be foreground or background stars to the cluster. All right, but see all the stars, and this is what shows them very well. This type of approach, when you actually let the stars drag for a little while. And now what I can do is turn back on the tracking. Okay, so pow, on comes the tracking. There we go. And when I come back to our main view, we have Praesepe back here, and probably should move it if we want to continue imaging, but let's go someplace else. So let's do this. And I can't go too late tonight because I do have to get up early to fly out of Connecticut and head down to Arkansas. Let's go check out the Golden cluster. We're just going to hop along Cassidy tonight, I'll tell you that. So here we go. Moving to the Golden cluster. And the telescope is moving, as you can see. There we go. The Golden cluster is not nearly as populated with bright stars as Praesepe is, but that's okay. So let's go eastward a little bit.
May I mention?
Yes.
Praesepe, the Beehive, was known to the ancient Greeks as a naked eye object. That's where the name Praesepe comes from, in Greek.
Okay.
They saw. Well, they didn't see a star cluster. They saw a little smudgy patch of light up in the sky between Leo and Gemini, and they called it Praesepe.
Yep. That's pretty cool. And do you actually know what Praesepe means?
I knew, but I forgot.
Okay, so
I want to say like herd of sheep or something.
Okay.
I forget.
Fair enough. We have listeners that can tell us. And viewers. Okay, I think we walked a little on this one. We did. I wasn't. I should have waited a little bit, but I didn't. Let it settle down, and now we'll take a 20-second shot at 12,800 again. Excuse me for coughing, guys. I do have a cough that I've acquired. I hope it goes away before my talk on Saturday. And it looks like I'm going to be in Arizona in June too, doing more talks. Ooh, look at that!
Kiss my grits. Praesepe is Latin, not Greek.
Okay.
So there's some mud on my face. But yes, it means manger.
Okay. Now see this. This is a classic bump, a classic bump. We have stars that suddenly got dragged out, and that shows that they dragged for the last part of the exposure. It actually makes a pretty shot. It looks like a bunch of speeding comets or meteors in the sky. But to an astronomer, that's an embarrassment. But we'll try again. Yep. Yes, sir. JG Marley, good to see you. Thank you for coming out. Papa Tom's here. Hey, how you doing? Good to see you. Papa Tom, you during our earlier talk with Daryl and Amanda and I, you had a question that apparently went unanswered. If you want to let me know what you were going to ask, I'll answer it here, if you like. Oh, here's that beautiful little cluster. This is the cluster that we're looking at called the GoldenEye cluster right here, otherwise known as NGC 2682. Okay. And so let me know, Papa Tom, what you want to do with that. I'm happy to answer it here. I didn't forget. I did not forget. Now that's pretty. Isn't that pretty? Yes, it is. Okay, so let's go on to the next object up for bids. Alright, so let's see. Here's another one called the Beehive cluster, but it's not really. But we have this little planetary down here I want to check out too. All right, and this is where's the planetary? It's not that. That's a star that's showing. Oh, the planetary right here, NGC 2610. Yeah, this is a little planetary nebula. And I want to check it out and see what it looks like. The telescope's going to go down pretty low toward the horizon, so I'm not expecting great things here, but we'll try it out. You know? So here we go. Oh, we got the dome. I can see the red of the dome here. So let me go back and see where that's facing. And let's go. Let me see if I have what I gotta do to make that right. Oh, I see what I gotta do. Okay. So, Daryl, can you handle things while I go move the dome?
Sure.
Okay. I'll be right back then.
Very good. James, I don't think I knew they made a 14-inch edge. I was aware of the 8, the 9 1/4, and the 11. I guess they're up in their game, though. I know with the those Roe Ackerman Schmidt cameras, they've come out with big ones now too. Those are really expensive. I don't know what to say. Wish Amanda was here. Easier to talk when she's here, or just let her do the talking. This time of year always makes me sad because all the cool stars of winter are going away, and they're setting or already have set for Mark already. They'll be setting here in an hour or so. Orion and Sirius and Canis Major and Aldebaran and Taurus. If you catch them before they set, they all set pretty evenly across the southwest to the west-northwestern sky, about the same altitude above the horizon. That means the mountains here, but you still see them just barely above the profile of the mountains. But then again, the spring stars are coming up now, and if you stay up late enough, you'll start to see the summer stars coming up. And you give it a few months, and hey, it'll be summer, and the stars of summer will be up in the sky. And if you can't see Orion, well, Sagittarius is the next best thing.
Okay.
Hello, no life.
What's that?
I was just saying hi to No Life 2692
Oh, yeah.
in chat.
Hey, No Life, how you doing? And VRZGG. Well, how far are they from us? We're talking about a meteor shower, right? Well, they're going to be about 100 miles.
Hello, David Schmidt.
Dave Schmidt, nice to see you. Yep. Okay, so I think we now can see this. And I see we do see stars. So I'm going to do 20 seconds at 12,800 right here to see if we can see this. But first, I'm going to go eastward. This is a little compensation factor I know that I have to put in based on the fact that the alignment needs to be reworked a little bit. Won't be bad, though. For those just joining us, I will be away for the weekend. I have to go to Arkansas to do a talk. It'll be on exoplanets and alien life, and extraterrestrial search. And I will also be talking about the black hole at a conference that will be down at Eureka Springs. Wow, look at that little thing right there. Holy cow. Let's go check that out. See it, Daryl? That's the very faint nebula. I don't know if you were talking because you might have been on mute again.
No, I'm not on
oh,
mute.
okay.
I'm just sitting here watching and listening.
Okay. It said something I didn't hear you, so it's okay.
Oh, no worries.
That's okay. Yeah, there we go.
Yeah, Eureka Springs, God, I forget which one is which down there, but I want to say that used to be like a big mafia hangout at one time.
Really?
Yeah, it was a pretty racy place back in the day.
Wow. No idea. Yeah, it's a beautiful little planetary down. This is low in the horizon, which is why you get all this modeling in the sky. Unfortunately, you know, that's just the way it goes. Let's see about, you know, I'm actually in a place now where we can actually go look into Leo now. We should be able to look into Leo and see some really cool things. I think we'll be able to see some of these galaxies for sure. Any idea, Daryl? Before I know we want to look at the triplet for sure.
The usual suspects.
We'll get to M87
the
a little
triplet,
bit.
the hamburger, M66, M65,
Yeah.
M96, and 95.
Yeah, that's down here. Yeah.
Yeah, and I think if you're in the neighborhood, you ought to look at the. I think we looked at it last week. M3 Globular. That's a spectacular globular.
Oh, it was. Yeah.
That'll be up in Coma, I believe.
Yeah, that's gonna be up here.
Coma Berenices.
Yeah. Oh, that's the Big Dipper. What am I doing?
Yeah, just to the
Right
left of
here.
Denebola there.
Yeah.
Right there.
Yeah, I don't know if I can go. That's M53. There's M3 over there. I have to wait because I remember we were looking at Pallas. Pallas was the asteroid that's here. Okay, but we can't look there yet. We're nowhere near these guys yet. We have to move the dome one more time. But I went outside.
Right.
I noticed clouds coming. Number one. Number two, the dome was literally dripping with water. But I have a system that prevents dew from getting on the corrector plate. So we are okay. Okay. And now I will prove it. So I'm going to go check out the Leo triplet. We're going to check out this guy first, M66. All right. And we're going to go here and check it out right now. And here we go into the wild galactic yonder. And we can see things moving for sure, no doubt about it. All right. And I'm not sure why, but tonight the dome cams, they don't want to lock in. Don't know why, but they'll probably work once I restart them. But I don't want to go out there and restart them. It's cold out there. Okay, and this dome cam here, we're actually riding along on the back of the telescope, and this is the one looking from the inside up at the telescope over our heads, so that's cool. Alright, so let's bring up our telescope control system, and we're going to turn this off and move eastward a little bit. And then
Papa Tom is posing a question. He asked.
Is that the one
he says last night? I thought he did it this morning about.
I think he did. Yeah.
Yeah, I asked last night about black holes. If iron kills stars, then what elements couldn't kill a black hole? I would say nothing can kill a black hole.
Well, no, but that's a very good question, I think, and let's handle that. So, where did he ask that? He said iron can kill stars. Well, is it up above somewhere or down below?
I see it down, and it's moving fast. Well, I lost it now. Everything's moving. Oh, there he is. He's about a third of the way up from the bottom of the chat.
Oh, there it is. Okay. If iron kills stars, what elements can kill? Okay, actually, you know what, Papa Tom? That's actually a good question. And while we're doing a 20-second exposure at 12,800 of these galaxies, I'll tell you. So, here's what happens. The elements in the periodic table all give off, upon fusion, they actually require less energy to fuse than they give off. Except when you get to number 26 in the periodic table, which is iron. At number 26, that requires more energy be put in than it returns. Ooh, this is beautiful. Look at that. Oh cow. Let me just give them their own stage. Look at that. Wow. Ah, look at that, Daryl. Look at M66 right here. Look at that.
See the spiral structure. Nice.
Yeah. So, Papa Tom, to answer your question, so iron will build up in the core. And iron, as far as the star is concerned, is inert. It doesn't go to anything beyond, no matter what the mass of the star. Because iron, again, requires more energy to fuse than it returns. So a star can't cross over that barrier. So this becomes stuck in the craw of a star. And when you talk about, say, moving, into the periodic table, saying you get more elements, well, how does that actually happen? Well, there's a number of ways that actually happens that we get more elements. Certainly, supernovas generate immense, astronomically, cosmologically massive pressures that can cause an instantaneous fusion of certain elements to become higher end elements. But believe it or not, stars like the sun and stars along the main sequence of stars like the sun have another process that they use to create a majority of other elements in the periodic table. And that's called the S process, which stands for a slow process. And here's in essence how it works. Let's say that you're a particular atom, and let's say that you end up acquiring an additional neutron, a neutrally charged particle in your nucleus. That makes you a different isotope. In other words, it's a different flavor of the same atom. So carbon-12 is a different flavor of carbon. Carbon-14 is a different flavor of carbon, but it's still carbon because it's the number of protons that a carbon atom has plus these additional neutrons that actually increase the atomic mass but don't add a change to the charge. Now, these are called the isotopes, and some of them are stable, okay, and can stick around for a while, but some of them are not. Many of them are not. And so they can decay. And this decay can sometimes result in a neutron over a long period of time being converted into a proton. Okay? Because neutrons and protons are made of quarks. Even smaller elementary particles are made of 3 each. And the quarks have a quality called up or down. It's a strange world we live in with quantum mechanics, folks. And if you can change the direction of quarks, or if the direction does change, sometimes a neutron, which I'd have to just calculate it out in my head here, is like one up and two down quarks, and you change one of those down quarks into an up quark, it's a proton, which is like two up quarks and a down quark. So that little change can now give you an additional proton in your nucleus. And now, what does that mean? It means you've got a new element further down the periodic table. One more. And it has to do with this decay that goes on sometimes, where you can get these additional neutrons converted into protons. It's a neat process called the S process, and it's it's a slow capture process too, where it takes a long time for this to happen. But you know what? The universe has time aplenty. So that's how we get more elements in the periodic table beyond iron, okay? Along with the supernovae, along with colliding black holes, along with emerging neutron stars. We get, with emerging neutron stars, we get things like gold. That's where our gold came from, believe it or not. A lot of it. So that said, what do we do now about black holes? Well, black holes, you see, those are stars. The original stars were much larger, more massive than the sun. And when they collapsed after running out of their nuclear fuels, they probably went supernova, okay? Because that iron core was just like a rock in the throat of a star. And the entire outer core around that core of iron basically all collapsed at once when the nuclear fuels ended. And guess what? That can happen in as little as a quarter of a second for a big star. Imagine that. And when that happens, the star it rebounds off that core, and because it can go nowhere else, in the process making more elements of some, and then blowing out into the interstellar medium. And when that happens, okay, the process continues. These elements go out into the interstellar medium, and the shock wave of their exit from the star can collide with other matter and form condensations along the way, where more stars get formed along the way. This happens in other nebulae as well. So, but the thing is, when you look at what happens to the star now, the inner part of that star that's left after all these immense pressures could have been shoved way past, depending on the mass, way past white dwarf stage, and actually beyond neutron star stage. And what's left? What's left is when you can get a collapse beyond a neutron star, where you have neutrons that are on the surface of the star. The whole surface of the star is hard as a billiard ball, okay, but it's hot ultraviolet radiation. The neutrons have their own pressure pushing back. So a white dwarf has electrons that are pushing back. That's electron degeneracy pressure. Neutron stars have neutrons that are pushing back, all right? Because all of the surface has been converted into these neutrons, and so it's neutron degeneracy pressure. But sometimes if the star is even more massive, then the collapse continues, and right past electron degeneracy pressure, right past neutron degeneracy pressure, and then you reach black holes. So the fact of the matter is, the black hole is probably the true end state for very massive stars that have gone supernova. All right? And there's no doubt about it that the black holes are exceedingly dangerous to be around. We probably wouldn't survive trying to go to one and just explore it. In the movie The Black Hole, they would have died far away from the black hole from the radiation exposure too. Black holes give off copious X-rays, and so those would go coursing through you and through your ship. No matter how much shielding you have, they would actually heat up the ship because the temperatures would be so hot. That's to say, so many high energy particles would hit the ship that the surface of the ship would absorb that. Because in space, there's no temperature per se. There's only absorption of radiation and emission of radiation, right? And those X-rays would strike the ship and heat up the structure of the ship tremendously. And I don't know any cooling system that could survive the heat of heating from that kind of energy, that kind of energetic material hitting it. So you have to just accept the improbable with that particular movie. Anyway, besides, it was made by Disney, so of course it was going to work out, right?
Sure.
So anyway, that's kind of the way that works. So a black hole is the end state for almost any large star that goes supernova, possibly beyond neutron stars. They're very massive. There's really not a whole lot that can kill a black hole in any way, shape, or form. And there's really no analogy to say, well, if iron kills this, then maybe this, maybe that can be killed by, something in addition or something else. And the answer is that not really. That's not what this is about, unfortunately. So that's just kind of the way it is, And I'm going to go to another location now. If that didn't answer your question, let me know, Tom, because I would like to answer it thoroughly for you.
Would it be fair to differentiate between the statement that iron kills stars versus iron kills fusion? Under normal circumstances, if you can call anything like that normal.
Say that again. I missed that.
Well, he said that iron kills stars, quote unquote. Would it maybe be better to say that iron kills fusion in the stars? Or is that splitting hairs?
I don't think that. I don't think that actually iron kills stars. I think that iron is the end state in fusion for any star.
Yes.
So I guess in a sense, I don't know. And just really quick, Marianne, I saw that you're here. Very nice to see you. Marianne is helping to arrange a trip to Phoenix for me, actually, to go out there in June, perhaps, to actually do several talks out there. So I want to thank you for that, Marianne, publicly, for your work in helping arrange that. So whether iron kills stars or not, I actually think that it's just the end state in fusion, so it doesn't kill stars. The fact that it's there doesn't kill the star. The star is already going through its death throes when iron just issues the coup de grace that causes the star to explode. In fact, I should say, it probably isn't even the iron that caused it to explode. It's just reached the last fusible materials that it has in its confines within itself. So having the last fusible materials is what causes the star to die. Having none left, I should say, to fuse, because the star is then going to collapse violently. So I think that's really what we're talking about. So, and all the rest of the material that is within a star is, that's just something to, that you can possibly fuse if you can get it close enough to the core where the temperature can get hot enough, and the temperature jumps dramatically. They're called fusion thresholds. It's like 13 million Kelvin to start hydrogen into helium, but helium into carbon. Now you're jumping up to like 100 million Kelvin, and it actually gets into the billions. It's actually substantial. There's your hamburger galaxy, wimpy.
I will gladly pay you Tuesday for a galaxy today.
If I could have a hamburger today, I'll gladly pay you Tuesday.
Oh, not on your life, Winsky. Unhands me hamburger.
Popeye cartoons.
Yeah, me too. It was fun. As you can tell, I've kind of watched them before,
Oh, yeah.
Yeah.
Unhands me goyle, Brutus.
Not on your life, Popeye.
Oh, Popeye.
Yeah, I can't. Ever since my surgery and the ensuing changes to my vocal cord, where I lost the vocal cord, I can no longer do olive oil, which was sad. I used to do like 87 different impressions of cartoon characters and real people, and I was doing them, semi-professionally. I had a radio show where all I did was talk to myself for a couple hours, and they thought there was a whole bunch of different people until they figured out that only one voice at a time was speaking. But then I lost it because when I had the surgery, so it's okay. I don't mind.
I'm sorry, David has a question for you. Mark, so a neutron star is a star with an altered number of neutrons in the nuclei of its gases.
Well, the way it works is that in the degenerate state, the atoms, of course, are destroyed in a sense. They're separated into their components, okay? And protons and so forth can be converted into electrons. Into neutrons. And we end up with that overwhelmingly dominant neutron state in these stars under those temperatures, under those conditions and pressures. And the neutron star is a much, much more massive star than the sun. And you can have a neutron star that's up to about, I think 2.2 solar masses or so, beyond which it'll probably be a black hole. So between 1.44 and above, you can get a neutron star, and up to about 2.4 or so, or 2.2. So at that point, those are the realm of the neutron stars, and they are massive enough so they can collapse right past electron degeneracy pressure. But the neutrons that are converted in there on the surface, those are going to have their own pressure that are going to push back and hold the star up. And again, there's no fusion taking place at this point. This is just the degeneracy pressure of the existence of these neutrons at the surface. And as I said, the surface of a neutron star, you could conceivably walk on it if you could withstand the gravity, which you couldn't. It's as hard as a billiard ball, and when they merge, okay, like what we saw merging neutron stars, that merging neutron stars actually, what we think, are what generate a lot of additional elements, including gold. And that kind of explains why gold is sort of rare in the universe. This is the hamburger galaxy here. That's pretty, really pretty. I know I'm jumping around, but you know what? I like doing this because it's just a lot of fun. This is beautiful. This is really pretty. Yeah. Look at that. What do you think, huh?
I like it. Folks, that dark lane you see cutting across the midline of the galaxy, if you have a dark sky here and you go out and look at the Milky Way on a summer night, you'll see that very same sort of dark lane cutting through our Milky Way.
That's right.
One part of it is called the Great Rift, the something or other rift, I think. I almost called it a geographic feature in Africa, sorry. The Great Rift. But you'll see the very same thing on a dark night. If you have a good view of the Milky Way, you'll see that dark lane cutting right down through the
that's right.
bright lines of the galaxy.
Yeah, and to carry on what you said, it's the Olduvai Gorge of the Milky Way.
Oh, there you go. Yeah.
The Rift Valley.
I almost stopped myself in time.
You did, actually. You did. You made up for it. I'm the one that actually took the joke beyond where it should have. And I'm sorry if I confused folks. But yeah, there's that beautiful hamburger galaxy. It's stunning. And now if we back out a little bit, let's see where the moon is now in our wonderful planetarium. I think the moon is going to be right down low, and it is. See that? So we are now wide open with Leo over here. I want to check out, though, I'm going to come back to M96 and M95 over here because these are beautiful. And I'm going to just see if we can get them both in the field by going right here. Okay, so I can actually send the telescope to a particular object, or I can move it to a field, and that's what I've done right now, is move it to a field. Okay, so I'm moving it here, and I know there is an east bias that I have to induce, or it's not going to be centered exactly in the same way. So it's pretty much holding there, and so what I have to do, I can stop it here and move eastward. a little bit. Okay, and then that might have been too much. I'll move it back a little bit. Okay. All right, and now, yeah, look at it go.
Mark, excuse me just a moment, please. I'll be right back.
No problem. I'm noticing that. That's interesting, isn't it? That was a satellite I'm looking at, not the stars. Look at that thing go. Did you guys see that? Look at this. Oh, I gotta take a picture of this. We're actually looking at... This is amazing. Look at this satellite. We're actually catching a satellite that's actually changing in brightness. Look at this, guys. Because I saw stars that remained in place. And this was blinking. Alright, let's take a picture. 20 seconds. I want to confirm that I'm not nuts. I think we actually caught it could be a slowly tumbling rocket body, actually. So we should see that it brightens and dims, and we should see a star out here that stays the same. Unless I've been fooled by this. I've been fooled before. You know, I've been fooled by imagery and illusion in the sky, but I saw one object. No, see, I was right. Look at this. Holy cow. Wow, this is amazing. So, yeah, we got a tumbling rocket body. Actually, you can see, look, it's bright, dim, bright again. We actually caught a tumbling rocket body right by M95, I believe. Let's go back to our view here. I don't want to lose this. Okay, there it is over there. Let's go bring that back in, because Daryl hasn't seen this. All right, so we're bringing it over again. There it is. Okay. There it is, right there. See it moving? Okay, that's a satellite that's moving through our field of view. And the weird thing is that we can actually see it. So I'm going to catch it moving by this bright star. You'll notice it's getting brighter again. Okay, let's go. Let me just bring it over again a little bit more. I'm sorry, I'm having fun with this. This is very cool. We're actually catching this satellite that's actually migrating through our view. All right, so here it is. It's getting a little dimmer. See it dimming out? And it freezes as it actually gets into the exposure. So it's going to get dimmer, then brighter again. And we'll see that. I thought I was going nuts. I thought my telescope wasn't tracking right. But it was. So it'll come up with our screen again here in a second. It'll come up with our visual. Okay, there it is. Look at that. See it? It dimmed, as I said, then it started to get brighter. This is actually kind of fascinating because it's showing you space junk. This is space junk out there, and it's actually it's a rocket body that was spent probably based on the speed it's moving. It probably is pushing something out into geosynchronous orbit. And look, it's almost vanished right now. So let's take another shot here. Where you can't even see it now, and then when we come in, it'll fade in. It was probably a booster that was used to send something out to that geosynchronous position. That's 22,000 miles away, and then what it did was it actually you missed it, Daryl, but you'll see it again.
Okay.
Look.
And hi, I'm back.
Look what we got.
Wow, cool.
You know what that is?
Satellite?
Yeah, but a different kind of satellite. It's a tumbling rocket body. Look, here it is.
Oh, okay.
Look at it moving. See it relative to the stars? See it's fading?
Yeah.
Yeah. Now watch, it's going to actually get brighter again, too. At least for a period of time until it actually enters the Earth's terminator.
Cool.
Yeah.
Yeah,
Here it comes.
I've seen those many times.
Here it comes.
Yes?
Yep. Yeah, and you'll see that it gets pretty bright. So we caught it a few times. We actually caught it going right by M95, I think. Well, there we go. Okay, so we've seen it. That's beautiful, guys. That was a fun little thing. Oh, there's our black hole here. Let me just get rid of this. So I thought that was pretty cool. So let's go back to M95 here because M96 I mean, because we were there and I allowed it to go away. So now I'm going to bring the telescope back there, because what I did was I put it on the galaxy and noticed right away that as I put it onto the galaxy, that I had this object in the view, and I thought, and it was moving, and I thought that, oh no, I've actually, my telescope's not guiding properly. And it wasn't that. And so we did the hamburger, and this is what I did. See, here it is. Here's the M96, right? And this is what I saw. This object moving slowly, and I thought, what the heck? There's something going on. But, and Amal asked the question, how do we know it's not a UFO? So how do we know? Well, because it's actually just regularly pulsating like this. This is a slow tumbling rocket body. So as it glints the light, we see it, and then it starts to turn, probably face on to us, or nose on, basically, just a cylinder onto us. So we don't see as much, and then it spins the other way, and we see more of it. This is before it got really bright again. And if we took a long exposure, we'd see even numbers of darkish and bright areas. Okay, but boy, that was cool.
That is cool.
Yeah, and again with M90, was it M90? What am I saying? M96? Was it? Yeah, it's M96. So with M96 there, it's actually pretty cool. I really thought that was pretty neat. And then, so that's what it looks like with some processing. Not bad, huh?
I think that's great.
Yeah, that's a kind of a neat little thing. And the weird thing is, you can see it's got some size to it. Now, of course, we walked a little bit, but with a satellite trail, you don't care. So that's the first time I've ever had that happen as it comes through our field. That's pretty cool. You know, it's actually a nice picture of M96 too. Look at that.
Yeah.
The galaxy looks beautiful. How nice. That's really nice. Okay, so now,
Mark,
yeah.
I'm sorry. Papa Tom asked another question. He says, Mark, Albert Einstein said the black holes have hair. What was he talking about? Question mark.
When he said that black holes have hair, I think he was referring to obviously not real hair. I think he was referring to magnetic properties, but I can confirm that because that's a colloquial term. I'm not sure, but I will definitely I'll look into that for him. And D. Smith, you said 231411 Zone 5. Is that the satellite? Let me know. It might have been Hawking. Yeah, that's the thing. I have to find out for sure, because
That's kind of what I was thinking.
I know the term was, I'm confused when you said it was Albert Einstein. I don't think it was Einstein, because it was probably more more of a modern take on it. But
I agree absolutely.
Well, we can find out.
Hawking was my first thought also.
Okay, we shall find out. All right, so what have I got here? Okay, so M95, and I want to go up here too. These make a beautiful trio up here, and I want to take us up here too. There we go. All right, and now we go there. We're pulling in. All right, pulling in. Boy, it doesn't take much to get me all excited, doesn't it? I see a satellite, wandering through, and I'm thinking, oh man, and I thought my telescope wasn't tracking because there weren't any other stars other than the one I saw. So I thought, why isn't this tracking? Then I saw a star. I'm like, wait a minute, that's a satellite. And it started to dim, and I realized, oh, it's a tumbler. That's even beautiful. That's even more beautiful. So I thought that was really pretty, and it really looked great. So I move over and a little down, and now we should have that trio right in our view. Don't you think there, Daryl?
Yes.
So 20 seconds at 12,800. Yeah.
Yeah, somebody... I'm sorry, I got distracted for a second.
That's okay. That's okay. Alright, so let's check this out. No, the hair thing was Stephen Hawking and Malcolm Perry. Okay, this has to change over here. There we go. There are the 3 galaxies. And I don't think it was magnetic properties, actually. I think it has to do with degrees of freedom. And I'll have to just look at that to figure out what they meant by that, because I thought it was something else. So I'm glad that you mentioned it, because I had a misconception going on there, and I'm not afraid to say so. You know.
I'd heard the term before, but it had been so long I didn't remember what it meant.
Okay.
I assume Hawking was speaking as an illusion, not illusion, but allusion.
Yeah. Yeah, I think it was more of a statement that had to do with degrees of freedom within a black hole. And he called it soft hair. Well, that's very interesting. I'd have to check that out. Well, see, this goes to show you, I can't always get it right. Anyway, but that's all right. I don't expect to. But you can be sure that I'll understand what you were talking about next time and be able to explain it to you a little better. You know, it's like anything. You know, you learn new things. Even you never stop learning. You know, black holes weren't my specialty, but they were just something that we understood to the level that we knew them. But I never actually spent a lot of time postulating about black holes. I was more of a exoplanet guy from the get-go, you know.
Yeah.
That was me. All right, where are we going to go next? Where are we going to go next? I don't know. Where are we going to go, Daryl?
M87.
Oh, yeah. Well, I have to move the dome again, probably.
Well, okay, hold on.
No, oh, that's okay. I mean, you never know. I might have it just there by now. Not sure. That's an essay. That's gonna be tightly wound. That galaxy's just too tightly wound, I'm telling you. And there's the kick the can. Remember we looked at that? And then the blow dryer galaxy made no sense to me. Let's try and look at M98. I've wanted to see that lately, and I haven't been able to. But I got a chance now, so let's check it out. This is an SAB. This is a Bard's Spiral, I think. I think we looked at this one time before. Do you remember?
M98 or M99? Which is that?
No, this is me. M98, yeah.
Yeah, okay. I don't remember. This is in Coma, right?
This is in Virgo. Or is that just over the border at the Coma?
Okay, yeah, well...
This is over the border at Tacoma, yes.
Yeah, okay, that's Coma right there.
Yep. Yep, yep. All right. I thought that it was still in Virgo at that point, but that's okay. Okay.
Oh, we've looked at so many galaxies in this part of the sky.
I
It's
know.
hard to keep them all straight.
It is. 'Cause
They're all cool to look at, though.
I don't mind not having all the answers about these galaxies. Let's do 20 seconds at 12,800 here. I could probably start climbing on the ISO a little bit now that the moon is gone. But wow, we've been going 2 hours already. Can you guys believe that?
Oh, yeah.
That's amazing.
Time flies when you're having fun.
That's no doubt. No doubt. Oh, look at that. That's just beautiful. Yeah. Look at that. That's pretty stunning. And there's probably more I could do on that one. But let's go see what else we have. I love, there's so many that you just want to look at more and more and more and more and more, you know what I mean? I would actually like to find the place where we can find the most galaxies in one field. And it's going to be here in Virgo somewhere.
Yeah.
You know?
Oh,
Well, down below in Virgo. It's going to be down here somewhere. Indeed.
where would you call the central part of the Virgo cluster? I would assume someplace near.
M87?
Oh, yeah, the Virgo galaxy. There.
Yeah. Well, let's go check it out and let's see what the Virgo galaxy has for us today. And this is the galaxy that we saw in the news today, so this is actually a great place to bring us to. And let's go check it out. And let's hope that I don't have a dome in the way, because I don't want to have to go move it. Let's just do it. Okay, it looks like we're okay. Looks like we're okay. Yes, indeed. We're okay. So, that said, let's bring up our telescope and go a little eastward here. And then do a kick to the west. And we should be covered now. So, we'll do 20 seconds at 12,800. Actually, 12,000 goes to 16,000. Another stop.
I just know we're going to get a really good look at that jet sometime or other.
We had a few. You know, we had a few views of it, the jet.
Mm-hmm.
Yeah. Yeah, we should be okay with the telescope. I think we've got a reasonable view. And we'll find out in just a second. Yeah, not bad. There's a slight, tiniest bit of dome overlap there. But let's check it out anyway. Okay, let's do this. We'll go back to our wonderful view here, and we'll leave that on. Then we'll go this guy, bring it up a little bit. Go east a little. Alright, and then kick it. Okay. Now we'll do, I'm going to do this. We know how this works. Let's go lower. Let's go to 8,000, right? Because we know that to see the jet, we have to actually go a little bit lower. So we'll do 20 seconds at only 8,000 ISO. I don't want to turn off the dome light. I want that dome light to show up, because if I see it, I know that I've got something interfering with the telescope view. It's sort of a kind of a little indicator light for me. Okay, there it is. No, look at that.
Yeah.
Can't miss it.
And, yep, right there at 2 o'clock.
Yeah, you cannot miss that. There it is, folks. There is that jet that's coming out from the black hole that we saw earlier, which was right here. This is the black hole that's inside of this galaxy right here.
Yeah. And as you said earlier, I think we may be seeing the beginnings of the jets in that black hole image there.
Yeah.
It may be rotated relative to your image.
Oh, yeah.
But the two lobes sticking out at about 10 o'clock and 4 o'clock, I think, those may be the actual beginnings of the jet.
And he's talking, of course, about these guys right there that you can see right here and right here. Mm-hmm. These could be the lobes of the jet, and we'll find out, won't we? And if you think about it, that would make sense, wouldn't it? Because the accretion disk would be perpendicular to those, meaning it would be going this way.
Right.
And look, isn't it brightest here? So it looks like we are looking at something that is exactly perpendicular. If this is the material coming toward us, and this is the material going away from us, if these are the north and south poles of the black hole, then obviously this would be where the brightest material would be for the highest energy in the accretion disk that's coming toward us and going away from us. So the accretion disk would be going this way in the view, okay, and the polar jets would be going this way. And I would venture a guess that this is the one that we're seeing at 2 o'clock. It's just flipped and reversed. That would be my guess. What do you think? Think my guess is reasonable?
I think that's a very good point.
So let's see what comes out. But I imagine that they might say that, because the weird thing is, though, this is kind of skewed a little bit from that position. So that means that could the accretion disk be warped around this black hole for other reasons? Maybe because the black hole is rotating at a high rate of speed. Because black hole rotation will cause some weird things to happen. So it's possible, you know. So we would expect it to be even here all the way around to here, but it's not. It's skewed a little bit, which implies that it's rotating more of an angle this way, with this much coming toward us and going away that way. And if this is supposed to be where the north and south jets are, out of the poles, then it could be that the poles are skewed relative to the accretion disk, which is not unheard of, actually. Wouldn't that be cool?
Yeah, I mentioned this morning, you know, if you look at Earth's magnetic pole and its geographical pole, geocentric pole, they are not aligned with each other.
Yeah. And Dee Dee, I'm going to explain it, because you know what? You're not suffering some kind of mental breakdown here of not understanding. Here's the way it goes, and I'm going to make it, I think, explainable that'll help you here. When we looked at our object we captured here, this is the galaxy Messier 87 right there. If we zoom in, there's a well-known feature on M87, which is this little jet of material coming out over here. It extends out quite a distance, actually, but we capture this much of it because much of it goes off in a different spectrum that you can't see with your eye. So this thing right here is a jet, and that jet comes from the fact that there is a black hole in the middle, which we saw today, and this is the black hole. And the black hole is actually a wonderful capture. We captured this round. This is actually the circular, disc shape of the black hole sphere that we saw there. And it seems to have an elongation here and an elongation there. And there's this bright material. So I'm just telling you what it looks like, right? Well, this bright material is because of material coming toward us. High energy material coming toward us, going around this black hole and going away from us over here. Okay, so it goes out of the page and into the page over here. So it's rotating around this way. Okay, so it seems to indicate that we have these magnetic jets, if that's what these turn out to be, that are responsible for those things we saw in the photo back here that we looked at. You know, where we actually saw at 2 o'clock in our image, we saw that there's this little jet of material coming off the side here. Well, if that was one side of the jet and the other side was over here, we didn't see, then see, those are possibly those jets, right? And if that's the angle it's at, then deep within the galaxy, of course, then that black hole that we saw, right, which is here again, then that means that this stuff here that we're looking at, this white stuff, we know that this is material coming toward us, okay, at a high rate of speed and orbiting the black hole. So it's all coming toward us and then going around the black hole. So it's doing this, you know, it's going around and around and around. Imagine this as going out of the page, into the page, out of the page, into the page. So toward us and away from us, you know, toward us and then away from us. Okay, and it seems like this is sort of skewed at a really funky angle, so that we're actually be coming out of the page this way, going into the page that way. So kind of like this. Okay, so into the page, out of the page, into the page, out of the page. And if this is those magnetic field lines, they'd be going at a weird angle to that disk. See, they wouldn't be lined up perpendicular, like going straight up and down. They'd be kind of going on a weird angle. So we're speculating that maybe that's what we're going to hear from them. But I just want to tell you, just because I value your opinion and what you provide for all of us here. So you're more than worth explaining this to. And if you still have questions, please don't hesitate to ask. I'm here for you, and I will answer them for you. Okay, as best I can, because you do wonders for all of us. And like I said, you're worth it. So that was what we actually were talking about there. So so that said, I think that the M87 was wonderful to see tonight, because we actually ended up getting to see it in real life here, and then in the real world of astronomy here. Just beautiful. Just amazing stuff. So I'm gonna probably we're gonna call it for now, and I'll tell you why. Because I do have to be up early. I got to fly tomorrow. I'm gonna be in Arkansas by 2 in the afternoon, and then I do my talk on Saturday afternoon at this conference. And it's going to be an hour or two of discussion where I'm going to talk about what I just showed you, the black hole. I'm going to talk about the hunt for extraterrestrial life. And I would actually be interested to show you the talk I did as well. So maybe I'll do the talk for you as part of the stream at some point. And I just want to answer Amal's question. He asked a great question. How's the black hole allowing the jet to escape? That's a very good question. Okay, what's happening is the black hole's jets are the result of material that is infalling into the black hole, and it's not actually entering the black hole. It's an energetic interaction with the area above the event horizon at the north and south pole of this spinning black hole. And there's massive magnetic fields on this object. You got to keep in mind, this object is billions of times, billions with a B, billions of times the size of our sun. Okay, it goes out beyond by several times, 2 to 3 times the size of the distance from the sun to Pluto. That's the radius from the sun to 3 times or so the size of Pluto, the distance of Pluto, and make that into a diameter. That's the spherical size of this monster, massive, supermassive black hole at the middle of M87. So that tells us an awful lot about this black hole. And so the magnetic field interactions at the surface of a black hole are just monstrous interactions. And so you will get these bursts of energy that follow the magnetic field lines that are emanating from this black hole, and they would come out not necessarily in the light range, but maybe in radio waves. And so that's why it's been often called a radio jet, for instance. But I think that this makes for an excellent endpoint for tonight. And I do want to thank all of you for coming out. If you have any last-minute questions, I'm here for a few more minutes. Daryl, if you've got something you'd like to add, feel free. I want to thank you for joining me tonight. It was very kind of you to come along for the ride.
Well, thank you for having me.
Sure. I mean, we did a nice 2 hours.
Thanks, everybody.
Yeah. Thank you, guys. So, again, a few more minutes. If you have any more questions, we will be happy to answer them. And if I missed the questions, then I apologize for that. Because I had, as you can imagine, I've got 10 things that I'm concerned about at the same time. You can see over here on my on the operations screen, I've actually got 2 screens up, and I've got an awful lot going on between the 2 screens that I'm actually monitoring to make sure everything is going along swimmingly, and it usually is. So I want to make sure that it keeps swimming in a swimmingly manner. So it's pretty cool. I want to thank you guys again for coming along. My next stream will probably end up being next week sometime, because I will not be here. And Sunday, SkyTour Radio is going to premiere with a informal discussion, which we already did, with Daryl, myself, and Amanda, where Amanda actually took the lead. It was basically Amanda's show. And she asked a bunch of questions about the black hole in M87, and Daryl and I talked about the black hole, and it went on for 2 hours and 10 minutes. We had to actually cut it down to go 1 hour, 56 minutes, and 4 seconds needed for the radio. So it was quite good. And so check it out Sunday night at 8 o'clock on kgraradio.com. And I will see the owners of KGRA tomorrow in Arkansas, because they're going to be there, and we're going to have some nice discussions as well. You know, KGRA is growing, and it looks like I'm going to be part of that growth, I hope. They said that there's a few shows that are doing very well, and ours happens to be one of them, and I'm humbled because it's all of you that helped make it that way. So I just want you to know that I am grateful for all that, and I'm grateful for your support. Thank you, guys. You humble me, so my hat is off to you, and I thank you from the bottom of my heart. So you guys have a good night, and I will talk to you again in a few days. All right, so enjoy the music as we fade out, and have a good night. And don't forget, keep looking up, guys. I'll see you later.
Good night, everybody.